Okay, this is a vector calculus practice exam. Um, this would assume that you're done with calculus 1, 2, and 3. So I'm going to go through this pretty quickly. And hopefully if you're taking vector calculus or if you want to review vectors, this is a help. Okay, so I'll let you snapshot this. There's 24 problems. Here are the first 15. If you want to pause, snapshot it. If you want to try this before we even go over it. And might as well put this over it. And then here are 16 through 24. 16 starts with finding the flux. I'm just going to adjust this. 24. D ends with verify your decomposition explicitly. So there's 16 through 24. So if you want to screenshot that, those are the problems that compromise the test. So this is a practice vector calculus exam. So let's get right into it. Okay, so problem number 1, if you screenshotted it, okay. 1, 2, and 3 on this page, we'll go through these very quickly because these are the basis problems. This does require you having a working knowledge of all the formulas. So if there's any formula you forgot, just go back, read over it, get it committed to memory, especially if you're taking a vector calculus exam this week or next week. Okay, so here we go. Number 1, let R of t equal this. We're going to find velocity and acceleration, then compute the speed at t equals 0, and then find the unit tangent vector. So all you have to do for letter A is take the derivative of each component of R of t. That gives you the velocity. Acceleration is the second derivative of the position function, so it's a derivative of velocity. So there's R prime, R double prime. You could do that quickly. I doubt you'll need much help for most of these, especially if you've taken the course. This is more of a review. These are the easy ones. Speed is the magnitude of the velocity. You wind up with root 5 for speed. And then the unit tangent vector is just your r prime of t over that magnitude of t. And you could leave it in that form. Some of these are going to be left in form where we're not going to bother to try to simplify. Okay, so that takes care of number 1. Number 2 is just finding the arc length here. From 0 to 1, and what we do first is we take the derivative, we find r prime of t, then we find its magnitude. We wind up with square root of 1 plus t squared plus t to the 4th, and what we're going to do is we're going to leave this integral due to no simple elementary antiderivative. If you had a calculator, you might be able to evaluate it, but this is fine. Arc length would be 0 to 1, square root of 1 plus quantity 1 plus t squared plus t to the 4th dt if you integrated that. So that's the setup. And we're looking mostly for setups with ones that have tedious integration or algebra. Okay, number 3, we want to compute the curvature and determine whether the curvature is constant. So basically what we do again, first step. First derivative, negative sine t, cosine t, 1. Second derivative, negative cosine t, negative sine t, 0. And then what we're going to do is we're going to take the cross product of the first and second derivatives. We set up our determinant here. We find the determinant here. This is stuff you're probably very familiar with from previous calc courses, physics, etc. We get sine, negative cosine, and 1. Now, what we want to do from there is we take the magnitude of that, okay, of those components squared. And since sine squared plus cosine squared is 1, 1 plus 1 is root 2. We get root 2. Okay, so the magnitude there is root 2. And if you go back, I wrote this in the lower left-hand corner here. The curvature formula is right here. You have the magnitude of the cross products of r prime and r double prime over the magnitude of r prime of t to the third. So keeping that in mind, if you were to just compute all of this, all of here, you're going to get your curvature is equal to root 2 over root 2 cubed. We did the most of the work, reduces to 1/2. And since that's a constant, yes, the curvature just comes out to be constant for letter B. So that's mostly mechanical and remembering the formulas for curvature. Little tedious, but not too bad. Okay, we'll move quickly through these. That was 1, 2, 3. Okay, let's move on to number 4. Okay, 4 is find the unit normal vector, n of t for the curve r of t, t ln t, t squared, t is greater than 0. And for this, we only have to do the setup. So the first step, we take the velocity, we find rather the velocity vector, which is r prime of t. Take the derivative of each component. You're going to get 1 over t, 2t. Second step, we want the speed. We take the magnitude of that velocity vector. We get the components. We're going to wind up with 1 plus 1 over t squared plus 4t squared. Third step, we want the unit tangent. Unit tangent, capital T of t, is the velocity over its magnitude. And then this is kind of just a conceptual question, like to get the unit normal vector, what do? We take the derivative of the unit tangent divided by the magnitude of the unit tangent. And we can leave it at that because the algebra behind this is quite tedious, along with getting the final answer. That's with the arithmetic. Okay, so moving along, number 5. And again, 4, all we needed was a setup. We're good with this. Okay. For number 5, we have this multivariable function f of x, y, z equals x cubed y, z plus sine of x, y plus z cubed. We want to compute del f, evaluate it at 1, 0, 1. This you could do rather quickly. You want to find the partial derivatives of each with respect to x, y, and z there. X partial, y partial, z partial. And then we put this in vector component form. Okay. Del f. And then we're just going to evaluate at the point given 1, 0, 1. And we're just going to wind up with this output 0, 2, 3 for our vector. That's all. And remember the del operator right here is I d dx, the partial derivative there of x, plus j d dy, partial derivative of y, plus k d dz. All right, that moves along. First 5 we could fly through. Okay, 6. Number 6, we want the directional derivative of f of x, y equals e to the x squared plus 2 at the point 1, 0 in the direction of a vector. So with the directional derivatives, you're given a function at a point in the direction of a vector. Okay, so this is a multi-step process. It's not too bad. And this is number 6 here. It cuts off right here, just to let you know. 6 cuts off right here. 7 is right there to find the equation of the tangent plane, but we'll worry about that next. So for number 6, you'll recall gradient. Get that first. Take the partial with x and the partial derivative of y. Those are the components of the vector there. We have that gradient. And then evaluate at 1, 0. You're going to get 2e comma 0. And then what we want to do is we want to find the unit vector. We find the unit vector. In this case, we're getting the magnitude. Negative 1 squared plus 2 squared equals root 5. That's from that vector right there. And what we're going to do is divide by that root 5. So it's a negative 1 over root 5, comma, 2 over root 5. And then what we want to do is find the dot product. If we get the dot product of this del operator with the vector, the unit vector, and make sure it's the unit vector, 2e dot times rather negative 1 over root 5 plus 0 times 2 root 5 just gives you the final directional derivative, negative 2e over root 5. That's all. That's all you have to do with that. Very straightforward, just remembering the procedure. Number 7, finding the equation of the tangent plane z equals x squared plus 3y squared minus 2xy plus 1 at 1, 1, 3. First thing you're going to do is find the partials again. Partial derivative of x is 2x minus 2y. Partial derivative of y, 6y minus 2x. Evaluate at the point 1, 1. Okay, because that's what we know about x and y. 1, 1. We're going to get partial derivative with x. It will be 0 at 1, 1. Partial derivative of y will be 4. Okay. So now if we want to get the equation of the tangent plane, we need to remember this tangent plane formula. Z minus z naught equals partial derivative of x times the quantity x minus x naught plus the partial derivative of y times the quantity y minus y naught. And you're just going to substitute what you know. Okay? So you're going to get z minus 3, because here's x naught, y naught, z naught. Z minus 3 is 0 times x minus 1 plus 4 times y minus 1. And it's going to just simplify to z equals 4y minus 1. There's your equation of the tangent plane. So these first 6 you should be able to hopefully fly through, especially if you reviewed. Okay. For 7, 6, 7. So we go to 8. Number 8 is a linear approximation. This one doesn't take long either. Use a linear approximation to estimate f of 1.02, comma 0.098 for the function f of x, y equals the square root of x squared plus y squared at the point 1, 1. Oh, so what we're going to do here, get the gradient. And by the way, we're going to choose f equals root 2 because if you substitute, take a look, both of these input values, if you substitute them in here, they both approach 1. 1 squared plus 1 squared is square root of 2, so that's where that f equals root 2 comes from. Get the gradient of each of these. Okay, so taking the gradient of each of those and evaluating at the point 1, 1, we'll evaluate at 1, 1. You're going to get 1 over root 2, 1 over root 2. Okay, now that leaves us in business. All we have to do now is once we have the gradient, we have our points. We're evaluating at 1, 1. Use the linearization. Set it up. Root 2, what we're approximating near, plus your gradient, 1 over root 2, x minus 1, plus your gradient here, component for the y, 1 over root 2, y minus that one. And what you're going to do is just now at the very end, once you have this linearization, plug in 1.02 for your x value, 0.98 for your y value. This cleans up really well, and you're going to wind up with root 2. Okay, so that's all for number 8. So we're making good time. Going fast because you could always pause the video, and these are more of the more straightforward ones. Number 9, find the maximum and minimum values of that function on the disk. X squared plus y squared less than or equal to 9. So for this, what you want to do is, in this situation, complete the square. We're going to complete the square, or we're going to isolate the x and the y terms. And if you recall what this is going to look like you may have done it earlier in the semester or in Calc 3, this is going to look like a paraboloid. This is the function, this function's a paraboloid on this disk here. And what we could derive from this is that the center of the paraboloid is 1, 2. Okay? Now you might not have a problem like this on your exam. I just threw this on here because it's interesting. Now the disk region here, x squared plus y squared less than or equal to 9. This is your r squared, your radius. So your radius is 3. Now, if we were to substitute this center point in here, 1 and 2, you get root 5. Root 5 would be less than or equal to the square root of 9. So root 5 would be less than or equal to 3. So you know that this is definitely confirmed. This is inside the disk. Okay? That's inside the disk. Now, we're looking at the distance to the origin. Your minimum here is going to be -5 at 1, 2. Think about why that would be. This is more of a think about problem. And your maximum, 0 occurs at the boundary x squared plus y squared equals 9. So your maximum distance occurs in the opposite direction, -3 over root 5, comma, -6 over root 5, directionally. And you're going to wind up with, if you were to take this going back here, if you were going to substitute 3 plus root 5 squared for this component, -5, you're going to get 9 plus 6 root 5 plus 5 minus 5, and you're going to get 9 plus 6 root 5, which would technically be our maximum. Now, something like number 9 being on an exam, I don't know if it would be on a vector calculus exam. This is more of like you're not really using calculus for number 9. And there's other ways to do number 9. You could arrive at the answer in different ways. But I just wanted to throw that on there. Think about it. This is a think about problem for number 9. Go back, look at it if you're interested. If you're interested in it. Okay, but number 10 is a much more likely problem that would appear on a vector calculus final exam because it does involve a key ingredient of vector calculus, of application of a Lagrange multiplier. So we're going to use Lagrange multipliers to find extrema of this function, f of x, y, z equals x, y, z, subject to this constraint. So here's our constraint. Think of this as f, and this is going to be our g. X squared plus y squared plus z squared equals 3. So here's our f, here's our g. So remember with Lagrange, think differentiation, partial differentials, and in vector component form, we get yz, xz, xy. For del g, we're going to get, so that's for del f. For del g, we get 2x, 2y, 2z. So remember what we want to do is we want to set these components of the vectors from the partials of del f and del g equal to each other, except del g is going to have these lambdas in front of it. Okay, remember that? That's important. The lambdas go in front of the del g components. And we place the corresponding components equal to each other. And the nice thing we have here is by symmetry, x equals y equals z. If you look at that, it's just symmetrical. Okay, and that goes back to old geometric principle. And we solve for x squared. This would imply x squared plus x squared plus x squared is 3. And you get x equals plus or minus 1. And going back to the original function, f of x, y, z, if you plug in 1, 1, 1, you're going to get an output of 1. And if you plug in -1, -1, -1, you're going to get an output of -1. So the maximum has to be at 1, and the minimum has to be at -1. So recognizing the symmetry there, that x equals y equals z, saves some time, and that's how you do number 10. Okay, very useful Lagrange multipliers. Okay, number 11, 12, and 13. Okay, now we're into the integration portion. We want to evaluate on a closed curve x plus y ds, where c is the curve, r of t, comma, t squared, 0 to t to 1. So what you want to do first in this situation is you want to compute your ds. And how do you do that? First step here, you want to find r of t. Okay, r of t is 1, 2t. And I should have technically put a derivative there. Sorry about that. That should be a derivative, right? Take the components of t and t squared. We put r prime of t. Then we take the magnitude of it. This should look a bit familiar. You get 1 plus 4t squared. Okay? Now what we do from here, we want to substitute x plus y equals t plus t squared. Okay? Think about what we have here. X component t, y component t squared. So x plus y is t plus t squared. And when we set up the integral, we're going to get from 0 to 1, single variable integral, t plus t squared, x plus y, times your ds. What's your ds? Your ds is this magnitude of the r prime dt. Now, to save some time, if you were to do this by hand, if you split this up into two integrals, you could do the first component via u substitution, the second one via a table or using trig substitution. And just to save time, if you were to go through all that work, that basically this is end of calculus 1. This is, you see, trigonometric substitution in calculus 2. You wind up with that 5 root 5 over 12 plus 3/64. It's natural log 2 plus quantity 2 plus root 5. So just to save some time, and probably a lot of you could do these on your own pretty easily, or you could just do them on your own. Some people hate doing these, no matter if they've taken, I know there's people with PhDs who hate doing these. Some may have forgotten how, but some people love doing integrals. But it's good to practice that on your own. But there's the final answer. Oakley dokley, moving along. That's 11. Here's 12. Almost halfway there. Now you have f dot dr, and f is component y squared 2xy, and c is the line segment from 0, 0 to 1, 2. So in here we have a line integral vector field along this c. What we want to do, if you get in this situation, line integral vector field, you see something like this, the way to go is to parameterize. Let x equals t, y equals 2t. Okay, think about how we derive that from up here. We want x in terms of t and y in terms of t. Okay, now r of t then, y x components t, 2t for y. Again, take the derivative, you're going to get a 1, 2. Okay, now our f of t in components here, this is going to now be, if we write this in terms of t, right? We're writing it in terms of t. We're going to get 2t squared, comma, 2 times t times 2t in terms of t, x and y. And you wind up with the f of t is 4t squared, 4t squared. Okay, so now what you want to do, 2 more steps. What we want to do is we want to take the dot product of f and r prime. Okay, so if we take the dot product of f and r prime, we get 4t squared times 1 plus 4t squared times 2. We get 12t squared. And then the last step in this is we have an equation in single variable form t. We just want to integrate this dot product, 12t squared, from 0 to 1, and we just arrive real quick. We arrive at 4. Not bad at all for that one. Okay, so we're officially at the halfway point, although the first half of the test is easier than the second half of the exam, rather. Okay, 13. Determine if f equals 3x squared plus y, x plus 2y is conservative. If so, find a potential function. So these pop up a lot on Victor Calculus exams. So the first thing you want to do is you want to take these partials with respect to y and x. But make sure here, you want this px. Here's p, here's x. Your p component, take the partial derivative of y, we get a 1. Your q component, take the partial of x, we just get a 1. If those partial derivatives match, they're equal, we could declare this vector field conservative. And now what we want to do is we want to get a potential function. Now to get the potential function, we follow along these steps. First step is to integrate the p component. Okay, now we're integrating it. Here's the p component, 3x squared plus y. We're integrating p. If you take a look at it, we're going to get x cubed plus xy plus c of y. Okay, now if we arrive at this, this means we integrated with a dx, because this would be 3x cubed over 3, x cubed, and then the y component just becomes xy, and then we take the opposite of that, c, not of x, plus c of y. It's important, c of y. And now what you do after you integrate that, now we take the partial derivative of y of this. This cancels out. We get 1 times x plus c prime y. We match that with the q component. Here's the q component, x plus 2y. C prime of y equals 2y. That means c has to equal y squared. Okay, and the reason why is if we were to integrate c prime of y dy, we're integrating this 2y dy. We get 2y squared over 2. That gives us our c. That gives us our y squared. That's where that comes from. I just added this step. Some of you might be able to do that in your head. Some of you may be rusty with this, but so that's where this component comes from. And in the final answer, we get f of xy equals x cubed plus xy plus whatever that c of y was. The c of y we identified, well, c, y squared. Boom. Done. That's the first 13. Okay. We're moving quickly through this. Number 14, 15, 16. Let's do 14. 14, they give you a prompt. Use Green's theorem to evaluate x squared y dx plus xy squared dy, where c is the boundary of the square. 0, 1, 0, 1. Okay, so a lot of times they won't give you a prompt, but there's a problem at the end of towards the end of the test that makes you explain Green's theorem, when to use it anyway. So Green's theorem here is in 2 dimensions. Always think Green's 2 dimensions. Stokes is a 3-dimensional form, you could say, of Green's theorem. So here's Green's theorem over this region, double integral. We take dq dx minus dp dy. Those are partials. And we're going to integrate that times the dA, that area. So what we have here, let's identify p. P is x squared y. Q is xy squared. Take the partials. dq dx gives you y squared. dp dy gives you x squared. We subtract these, right? So it's this minus this. Y squared minus x squared dx dy. The bounds aren't bad at all. 0, 1, 0, 1. We could separate this integral. This is separable here and here, and then it's not bad at all. It comes out to 0. So all that work and we got nothing. All that work for nothing. Answer is 0. All right, 15. We want to evaluate this. X plus y plus z ds, where S is the plane, z equals 4 minus x minus y. Above, x is greater than or equal to 0. Y is greater than or equal to 0. X plus y less than or equal to 2. So the first thing in this type of situation, just make sure you graph a picture of this, what this looks like. Because it's easier to get our dA first to see if we could just get that out of the way. So let's get the dA component first. You get a triangle according to these bounds, and you're going from 0 to 2 on the x-axis. And just be careful here. Just because you're going from 0 to 2 on the y-axis here, by the bounds, you're not integrating 0 to 2. You're integrating from 0 to what this y is. And this y value, if you get it by itself, is y equals negative x plus 2. So that's important for the bounds of integration. And if we wanted to, this region, if we wanted to just take the area of it real quick, it's a triangle, 1/2 BH, 1/2 2, 2, 2. It's just 2. So we know dA is going to be 2. That saves us some time. So now what we want to do, use the surface formula for this z equals f of xy. So ds is going to be equal to 1, in this situation, 1, plus the second, plus the partial of x squared, plus the partial of y squared, and all of that is under a square root. The partials aren't bad. Partial derivative of x is -1, partial derivative of y is -1. And to get ds, we're just taking the square root of these components, 1 plus 1 plus 1. That's all. So 1 plus 1 plus 1, that gives you 3. So basically, what we have here, we have a square root of 3 dA. Okay, and now this whole thing, if we go and substitute, right? Substitute for z into this original, okay? Substitute for z. Put everything in terms of x and y. We get x plus y plus 4 minus x minus y. Those x and y's cancel, you get a 4. So here's the nice thing. Along this region here, it's the integral 4 root 3. And then we already have this area. We already know this area is 2. So all you have to do is shortcut. Boom, right here, 4 root 3. Okay, times 2. Area of the triangular region, multiply it by 4 root 3. Final answer there, 8 root 3. That's all. Okay, so that's 15. Hopefully a problem like that looks familiar. Okay, moving along to 16, we want to find the flux. Very important application, finding the flux of f equals x, y, z squared through the surface z equals 1 minus x squared minus y squared z. This should be greater than 0. Just to let you know, that should be greater than 0. Upward orientation. Okay, so my apology for that. Z is greater than or equal to 0. The surface formula for the flux over the graph, here it is. F dot ds along the surface. So this is 2d. And then f of x, y, z, you're dotting that with negative first partial derivative of x, first partial derivative of y times 1. Okay? So the first partial derivative here, with respect to this, negative 2x. With respect to y, partial is negative 2y. Okay, so our normal vector here is going to be 2x, 2y, and then a 1 component. Okay, don't forget the 1 for the z component. Okay, from what we have up here, there's our normal. We're dotting this with the normal, then integrating. Now from here, dot product f dot n, this is just basic here. We have x times 2x plus y times 2y plus z squared times 1. 2x squared plus 2y squared plus this, right? Plus this whole thing. 1 minus x squared minus y squared squared. Don't forget about that z squared. Okay? Don't forget about that z squared. Okay, so from here, to make it easier, when we have to integrate, convert it to polar coordinates. Okay, and the nice thing is when you convert this to polar, you get 2r squared plus the quantity 1 minus r squared squared equals 1 plus r squared. And that's because x squared plus y squared equals z squared. That's why you could do that. Okay. And x squared, my mistake, x squared plus y squared equals r squared. I meant to say r squared. My apologies for miscommunicating there. So we want to integrate over the unit disk. Bounds are 0 to 2 pi, 0 to 1, and quantity 1 plus r to the 4th. And remember, when you're integrating with polar coordinates, don't forget the r. Don't forget the r that we have to multiply this by, r dr d theta. And we wind up with, from 0 to 2 pi, that's just that 2 pi integrates, take that out. That could be done quickly. And then this, to integrate here, what happens when we plug this in, these bounds, we're going to wind up with 4 pi over 3 as the final answer. Okay, so I went through that quickly. You could integrate that. Okay, so that's the flux problem. And now we go into the Stokes component. Stokes, remember, 3D, think 3D Stokes, think 2D greens. So 17, use Stokes' theorem to evaluate this. Closed integral f dot dr, where your f is y, z, x, and c is the boundary of the disk, x squared plus y squared less than or equal to 1 in the plane z is 0. So use Stokes' theorem. Here's Stokes' theorem. Okay, and what we want to do, and just to save time, you want to compute the curl. Go back. Remember, the curl situation is the del operator, cross product of the del operator and f. You could do that on your own. You're going to get -1, -1, -1 for that cross product. The surface is the disk, where it's at basically your z value is 0. So automatically, if you're dealing with that, the upward normal vector has to be 0 and 0 for the x and y components and 1 for the z component. Okay? In this situation. Okay? Because of what we are given here. And now del dot f dot this normal vector. So if you did that's del dot f dot the normal vector, I skipped through the steps there because it's just arithmetic, equals -1. And now all you have to do, and this is pretty quick, not bad, integrate over the unit disk. If we're integrating over the unit disk, well, 1 is our radius. The trick is the area of any unit. Think of a circle of radius 1, the area is pi. So you're just integrating along s, -1 ds. So -1 ds in this component is just going to be -1 times pi. So you're going to get negative pi for this Stokes' theorem application. So it's not bad. Just remember going through the steps. This I left out some of the arithmetic stuff there, but I'm sure you could do it. Okay, moving quickly through here, number 18. Now use the divergence theorem to compute the outward flux of f equals x squared, y squared, z squared across the surface of a cube, and that's a unit cube, 1, 1, 1. Okay, those are our dimensions. So what we want to do first, if we're using the divergence theorem, it's the del operator dot f. So we take the partial derivatives with respect to x, y, and z, and times the del operator, we're just going to get 2x plus 2y plus 2z. And now, here's the nice thing. All you have to do if you're going across the surface of the cube, well, if it's a cube here, x, y, and z are just 0 to 1, 0 to 1, 0 to 1. So you could split this up into 1, 2, 3 integrals, 2x dx, 2y dy, 2x, that's a dz. And then you're just going to take the sum of the 3 integrals. It's not bad at all. You wind up from the divergence theorem, saves us a lot of time, 3. That's all you have to do for number 18, divergence theorem. Obviously, it could have been a lot more complicated with the derivatives and the arithmetic, but that's the procedure. Okay, so now we get to the more interesting part of the test. 75% of it done. We go to the last 6. Okay, so here's where we want to go into the concepts. 19 and 20 are conceptual questions. Okay, so let's stick to 19. We want to explain the geometric meaning of the divergence of a vector field. Include an example of a field with positive divergence and one with 0 divergence. So this requires that you study your notes, textbook, study online, and really understand what divergence means so you can explain it and provide examples. So here's what we could say here. Basically, a divergence measures how much a vector field is spreading out from a source, okay? Or compressing inward, sinking at a point, okay? And now for a positive divergence, the flow, what it's doing, it's not coming in. Positive divergence, the flow is spreading out from a source. So think of like a creation. It's spreading out from a creation in this situation. And for a negative divergence, the flow is converging, it's sinking, or it's disappearing. Now, the third situation we have is a 0 divergence. If there's 0 divergence, there's no net flow in or out. So we call that, remember that this is a key word you'll hear a lot of people say, it's incompressible. So the fluid density in that situation is constant. All right. So that's basically what you could just classify divergence as geometrically. Now, positive divergence and zero divergence. So positive divergence, if we were to think of something that positively diverges, the most basic thing would be x, y, z. All three are positive. And the reason why is if you took del dot f, think of divergence theorem, del dot f, you get a positive divergence. 3 is greater than 0. So what would that mean? That would mean if you get a positive divergence, the vectors point outward. They point outward. Okay? Now, on the other hand, if we were to figure out a zero divergence, if we were to use this, we want at least one to be negative, one to be positive. And if we fix the z value with the z component at 0, this makes it an easier way to describe this. If we were to take the del operator and dot it with f using the divergence theorem, if you were to go through the arithmetic there, you get 0. Okay, so you're going to get this is fluid spinning, pure rotation. So this zero divergence basically means you're going to get pure rotation around and around, no net expansion inward or outward for zero divergence. Okay, so that takes care of that. And go back and study, be able to explain that in detail. Okay, 19 is, it's good to have conceptual questions like that. 20 as well. 20 is also conceptual. For 20, they want you to compare Green's theorem, Stokes' theorem, and divergence theorem, explain how they are related and what dimension each applies to. Okay, so let's go over these. So just setting up a chart here. Theorem, dimension, boundary, interior summary. So Green's, do this first. 2 dimensions, bounded curve. Area, that's interior. And here's the summary for Green's. This I'll say it because you could enlarge it, but the circulation around C equals the total rotation inside. Okay, the entire region. So the circulation around C equals the total rotation inside the entire region. And what Green's theorem does is it converts a line integral, a lot of them could be very messy, to a double integral. That could be much less messy. Okay? That's the basis of Green's without drawing the picture. Stokes, surface 2D in 3D. 2 dimensions and 3 dimensions. The boundary here is also a curve, like Green's. The interior, though, unlike Green's, the interior is a surface. Okay? So, what this, we could summarize Stokes as a circulation around a boundary curve equals, think curl, a total curl over the surface. Basically, what that does is it generalizes Green's theorem to 3 dimensions. That's what Stokes' theorem does. There's a lot of great video tutorials, video lectures on the internet with that, and a lot of textbooks explain it very well too, if you want to go into more detail. But remember, this is just a practice final exam for vector calculus. We're not going into the gory detail of everything. Now, divergence, dimension, 3 dimensions. Think divergence, think volume. The boundary is a surface, an entire surface. The interior, we're looking for the volume. And here's the summary for divergence. Think flux. Flux out of a closed surface equals the total divergence inside. And what that does, it converts the surface flux to the volume expansion. Okay, so that's what divergence does, divergence theorem. And one more note, okay, they all convert a boundary integral into an interior integral. So that's at the bottom here. They all convert a boundary integral into an interior integral. So that's important to note. Okay, so that's number 20. So 20, and moving along, 21, back to numbers and letters. So 21, a velocity field of a fluid is given by f of x, y equals that y comma negative x. We want to compute the circulation around the unit circle, x squared plus y squared is 1, and interpret the result physically. So for number 21, what we want to do is start out using Green's theorem. Okay, so here, what we want to do in this situation, take the partial with respect to negative x minus the partial with respect to y. I should have had that y in parentheses. Okay. Now when we do that, we're going to get negative 1 minus 1 dA. And the region is just negative 2 dA. The curl is negative 2. And as a reminder, the area of the unit disk, area is pi r squared. So the area of the unit disk is just going to be pi. So that's going to be our d. This is our dA, pi, right? That's our area, rather. So what we could do here, close circle, boundary, f dot dr, integrate here, negative 2 dA. Well, here's the nice thing. We know that the region R is this unit circle, and that area comes out to pi. So all you have to do is multiply negative 2 by pi. So another little shortcut there, we get negative 2 pi as our circulation around the circle for that velocity field of fluid given. Now letter B, we want to interpret the result. And what does that mean? So take a look for letter B. Here's what it means. The field is going to rotate clockwise. So verbally, let's think about this. It rotates clockwise because it's negative. Remember, if it was positive, it would be rotating counterclockwise. Positive rotating counterclockwise, negative rotating clockwise. So this negative indicates clockwise rotation. The magnitude is constant, uniform rotation. And what you want to do is you want to think about this. This would be rigid spinning, and it would be rigid spinning clockwise. Rigid spinning clockwise. So it's going in the clockwise direction, not counterclockwise. Counterclockwise would be positive. Okay. All right. And moving along to number 22. Okay. This one isn't bad at all, especially if you could recognize that it's path independent. So 22, a particle moves in the force field F equals 2x, 3y, 4z along the curve from 0, 0, 0 to 1, 1, 1 along any path. Compute the work done. So it's a work application. And then explain why the path does or does not matter. So here's what we know. First, check if it's conservative. F equals... here, we integrate. We're integrating this. 2x, 3y, 4z. In components, we get x squared plus 3 halves y squared plus 2z squared. Okay. The nice thing is, this is path independent. The line integrals are going to, they work depending on the endpoints. We have very clearly defined endpoints that we don't have to worry about much in this situation. So all we have to do now is if we plug these in, work equals W of 1, 1, 1 minus 0, 0, 0. And you're just plugging it into this. X squared plus 3 halves y squared plus 2z squared. If you remember this, if it's conservative, this makes this problem much, much, much easier. So you get 1 plus 3 halves plus 2. Now plug in the zeros, minus 0. And you're just going to simplify this. Part A is 9 halves. Part B is recognizing what this is. Explain why the path does or does not matter. So this is more of a conceptual portion. Requires you, like, you read the textbook and the notes. And in this situation, if you were to take the cross product of del and f, okay, if you were to do that, here's f. If you were to take the cross product of the del operator and f, if you go back and do that, it'll yield 0, okay? And as a result, we could say the field is conservative. And if the field is conservative, there's a couple things we could determine. We can say with confidence in this situation, the work depends only on the endpoints. Okay? And think of work, force, displacement. Okay? In physics terms, in this situation, it was a clear path. And the path in this situation happens to be irrelevant. Okay, we're path independent. Line integrals work depending on endpoints. We're good to go with one like that. So that's 22, it's just for A and B. Almost there. We got 2 more problems to go. Okay, this is, whoops, a daisy. That's 22. Here is 23. Whoops. Sorry about that. 23. Let me get this out of the way. Oops. This is some comedy at this point. This was holding up nice before. Okay, 23. All right, so here's where we have an application problem. Let f equals negative del capital T, where T is the temperature function. T of x, y, z is x squared plus y squared plus z squared. We want to find F, then compute the outward flux along the sphere. And then what we want to do after that is we want to interpret the sign of the flux. Okay, so what this is in terms of temperature, this is a heat flow problem. We want to find F. So the first thing you do, again, think partials. Take the partial derivatives, x, y, and z. You get 2x, 2y, 2z. Then we're multiplying that by a negative. All right? That operator is f equals negative 2x, negative 2y, negative 2z. So that is it for letter A. Not bad at all. Now we get to the fun part. We want to find the flux across the sphere. X squared plus y squared plus z squared is r squared. So to do this, we want to use the divergence theorem, the del operator dot f, and that would be these components here. You're going to wind up with just getting a negative 2 plus a negative 2 plus a negative 2. So negative 2, negative 2, negative 2 gives you negative 6. Now the nice thing is that the volume of a sphere, radius capital R, that's just going to be 4 pi r cubed over 3. So that's our volume. Our volume's taken care of. This saves a lot of time. So the flux in this situation, double integral here of the surface, S, f dot n ds. Well, we did all this, okay? The f dot n, we get negative 6. The ds, the surface here in ds, 4 pi r cubed over 3. So we just take the product of that. Negative 24 over 3 is negative 8. We get 8 pi capital R cubed. That is our outward flux across the sphere. That's all you have to do for that. That's our outward flux across the sphere. So when we get to part C, we want to interpret the sign of the flux. Well, think about this. It's negative. If the flux is negative, that means it's inward. The heat is flowing inward, and this makes sense. Think in terms of physics, thermodynamics. The temperature is going to increase outward. And think about why it does that, right? heat flows towards lower temperature, right? Heat flows towards lower temperature. Think Newton's law of cooling, whatnot, thermodynamics, laws of thermodynamics, whatnot, what you learn in thermodynamics, and heat flowing towards the center. So that would take care of interpretation of the sign of the flux. So that's number 23. And we're almost there. One more to go. Last one, 24. Okay. Whoops. So 24. We want to let. Whoops, this keeps flowing. Let me try this again. Sorry about that. 24. A little bit of comedy in here. Okay, so 24, last one. And I don't know if your professor would put one like this on the exam, but this is good. This is kind of fun. I'll walk you through it, and then you could like study it, break it down, whatnot. So we let f of xy equal this. Okay, e to the cosine y minus y, comma, negative e to the x sine y plus x. We want to compute the divergence of the scalar of f. Determine whether f can be written as a sum of the conservative field and rotational field. Find the scalar potential function such that part of f is conservative. And then part D, you want to verify your decomposition explicitly. So we want to show that it can be decomposed using some work. Okay, so part A is the most straightforward part. Compute the divergence in scalar curl. So here we want to make sure G has zero divergence in this situation for B. So this had to do with part B. See where I'm circling here with the pen? This has to do with part B. Going down to the divergence. The divergence is del dot F, and we're just taking those partials. d dx ex cosine y minus y plus d dy negative ex sine y plus x. This clears out very nicely. Terms cancel, you wind up with 0, so the divergence first part is just 0. Now the nice thing here is we have two dimensions, so the scalar curl, this component of f, we want to find dq dx and dp dy. Okay, now think about this. Here's p, right? Here's q, dq dx, negative e to the x sine y, right? And then dp dy, negative e to the x sine y minus 1. Okay? So here, not bad, right? Not bad. From here, let's see what we have. Curl, negative e to the x sine y minus e to the negative x sine y minus 1. We get a 1. Okay? And we get that 1, and that's constant. All right? So, we got the divergence, and we got the scalar curl. That takes care of part A. Okay, now, moving along, what do we have here for part B? Okay, for part B. For part B, we have F equals del plus this G, of our operator here, del dot G. Okay, now this is the standard Helmholtz type decomposition idea. I don't know if you went over that. If you did, that's great. But what this implies here, we have divergence equal to 0, and the curl is equal to a number that's a constant. So divergence equals 0, curl is not 0. So we're good with that. We know that. So F, okay, F is not purely conservative, right? It's going to be able to be written, okay, can be written conservative part here, rotational part here. We're going to be able to split this up into two parts because of this. Curl not being 0 and the divergence equaling 0. And because of, if you want to look that up, the Helmholtz type decomposition. So yes, such a decomposition exists. Okay. Now for letter C, we're going to look for conservative, we're going to find rather a scalar potential function such that part of f is conservative. So we're going to look for a conservative part. Well, if we do this, if we go back to what we did over here and we look at this function, we kind of think about it. If we take the partial derivative with respect to x of e to the x cosine y, okay, that gives you e to the x cosine y. And if you take the partial derivative with respect to y of e to the x cosine y, you get negative e to the x sine y. Okay, this occurs here, and this portion occurs here. So if we take the del operator of e to the x cosine y, right? If we take that del operator, we could write this as a vector, e to the x cosine y, negative e to the x sine y. Now, what this does, this matches part of f, right? This matches the x component here, and this part of it, matches the y component here in that part, right? Or we could say the I and the ij components, rather. However you want to think about it. As long as you get the right answer, you want to think about x corresponding with I, y corresponding with j, z corresponding with k. If you want to just think about it in the pieces where they belong, kind of. Just in terms of thinking about it. So the match is part of f. So since you have those matches and those components, we could say that xy here, for this function of xy, is e to the x cosine y. So this e to the x cosine y we could designate as a scalar potential function so that part of f is conservative. Okay? So we looked for a conservative part. There's our conservative part. Okay? That's the scalar potential function right there. This equals e to the x cosine y such that part of f is conservative. All right. And the last portion here, we have our g equals this difference. All we have to do here is use the manipulation of this. F is equal to this, so g has to be equal to f minus that. Yes? So, all we do is substitute. We know what g is, we know what this is, we know what this is. Go look at what they are. Substitute. Vector subtraction. After this, these clear out, you get negative yx. Okay? And if we're going to take this further, verify our decomposition further for this, we get this negative yx. Check the divergence of g. Now to do that is we take the del operator, dot it with g. Taking the del operator, dotting it with g, we get partial of d dx of negative y plus dx dy. And in those situations, we get a 0 plus 0, we get a 0. Okay? So, what we could say in relation to this formula's manipulation up here, f would equal this. So, this is a nice way of just like checking to make sure that, okay, you could verify your decomposition explicitly, that the everything matches where it needs to match in the very end. So that one was kind of fun. So that's it. Those are all 24. So that's a practice final exam for vector calculus. If you're taking an exam like that, hopefully some of this helps. Hopefully some of this might have even piqued your interest. And hope everyone has a great day. Bye-bye.